Hello, welcome to Lecture 10. Let us get started with the slides that I did not scroll to the top of. Alright, so first, the first half of this lecture is going to be a little bit more about pointers and things, and then we'll get into the heap. Alright, so the good, the bad, and the ugly about pointers. So pointers are quite nice. We remember the example where we're swapping things. They let us pass things around without having to copy anything, and that allows us to touch individual elements, pieces of memory that don't belong to the current function, or just an address that represents an array in this case. So if we pass AR to a function, we're getting its address, like AR is an address to its first element. It's the pointer to its first element. AR by itself is essentially address 100 in this example. And so if we were to pass that to a function, we're not actually copying an entire array, which is going to make things more efficient for us. And then it also gives us another way to talk about the same stuff. So AR0, because AR by itself is essentially address 100, it points to the first element in AR. AR0 is the same as star AR. Those are equivalent because you can pretend that AR, instead of putting it like right here, let's move it. Let's put it right here. AR is essentially a pointer to that first element, and you can maybe make even a box. It holds 100, right? Something like that. And that also means that you can do pointer arithmetic with that, because AR plus 2 is just 2 more ints after AR. So 1, 2, so it's the address 108, and so if we were to dereference that, it would hold 50. So AR at index 2 is the same as going to AR plus 2, the address, and getting the element there. Remember that it's plus 2 because the compiler is nice to us and it knows exactly how far we want to go, even if we say plus 2. We're not talking about bytes, we're talking about whatever type of thing that AR points to, go that width times 2. Okay, so in essence it's going 8 bytes because every int is 4. All right. So yes, we've used pointers to pass arrays into functions, and remember you have to pass along the size too. And then also we've talked about pointer arithmetic. So it's sometimes helpful in like a loop where you just have to say, my current index, or the thing that I'm looking at, is whatever it was plus 1, and then you can keep on dereferencing that. So just to get yourselves ready for your next midterm, this is the kind of question that you should prepare yourself for, drawing a bunch of diagrams involving pointers and things and arrays. So let's do this one, and maybe you can take a second to try it yourself. All right, so here's our array. Let's be economical. Let's put it over here. Let's use both sides. So let's just execute this line by line now. So we're going to make a diagram for this. And so the first thing that we're going to do is make ARR in memory, because that's what this line declares. It makes an array called ARR of length 3. And it holds 50, 60, 70. And then we have int star p, and initially p is just pointing out into space. So we'll say p is here. It holds some random address right now, so it's like pointing off into the ether, and if we were to dereference it, it would probably give us some kind of segfault for one reason or another. So then we can say p equals ARR, and remember, ARR is just really a pointer to its first element. So this was like address 100, 104, 108. Well, that makes p now equal to 100 and pointing to the same place as ARR by itself without any brackets is also pointing. So this kind of line is saying, let p hold whatever address ARR holds, and ARR is secretly a pointer to the first element of the array. And then we're going to change p, not star p this time, so just p, change p. We're going to change the address that it holds, so right here, to be whatever it is plus 1, and remember that plus 1 means one more int in size. So this is not pointing to the first element, or the 0th element anymore. It's now pointing to this. Maybe I'll draw a black line. It's now pointing to the first element, the 1th element, I guess, ARR1, or the second element, whatever you want to say. And then finally we're going to execute this line, star p equals star p plus 1, which is not setting p anymore, not the box p, but what's held when you follow the pointer p. So the memory value here is now going to get changed to whatever it was, plus 1. So this now becomes 61. All right, so familiarize yourself with these concepts. That's super helpful for your future labs and any other classes you have to take about that involve low-level memory stuff. Okay, so that's that. And we've already talked about pointer arithmetic a little bit. I think we've already seen, if not this slide, a slide that's very similar to it. So the idea is that the compiler is very smart. I just want to keep reminding you of that. And so a pointer plus 1 is not really going to the next byte in the memory address, but it's going to add the size of that element of the array. So if we had an array of structs, for example, like I had a bunch of points, like remember we had struct point. It had a double x and y. What did I forget? That semicolon. And so if we had this, and maybe down in our main function, we could start declaring arrays of points. That's totally fine to do. You can say point p is not p anymore. It's like, how about an array of 5 points, please? And you could initialize them if you really wanted to, but this is just an example. So you can have arrays of points, and they'd look like this in memory, but on the inside there'd just be a bunch of points now, and they would take up a lot more space than just one single integer, right? They're 2 doubles, so in essence they take up 16 bytes. And so if you had even an array of structs, the compiler would know how long and how wide one element of that array is. And every time you say ptr plus 1, if that was a pointer into some element of the array, ptr plus 1 would get to the next element. It would know how wide that element really is. So it knows things like it's 1 byte for a character, 4 bytes for an int, and that's why we're declaring all these types all around. So this kind of thing can be done for us. That's why I guess you can't do the same thing in Python, I guess. Or it's done for you. All right, so the ugly stuff about pointers, a lot of the things can go wrong, right? So you have to, going back to the types kind of thing, you can only have a pointer pointing to a single element of a type. Like you can't have, you can't say something like int star p equals ARR, and then you can't do something like int star p also equals ARR if ARR is a pointer to an integer and it's like an integer array. Like this doesn't type check, right? Because it's supposed to be a pointer to an int, not a pointer to an int. So there should be extra indirection. So you always have to be careful with your types. And so you only get to hold the address. Your pointers only get to hold the address of whatever one type that you declared that pointer can point to. Okay? Int star, char star, struct star, things like that. And then remember that things can go wrong if you don't initialize things. This is just another place in memory, PTR. It just holds a special new kind of type, an int pointer. And you need to make it point to something, or like set it to null, or alternatively allocate room for something new in memory, which we're going to talk about later today. Okay, so that's the idea. And then the ugly, if you want to read this yourself, people regret having pointers in languages. Like that was, people have decided that that was a bad idea. But it's sometimes useful, we've seen. You can run into a bunch of errors is what I'm trying to say here. And on the next slide after it, I'm going to give you a short example of how to debug pointer-related errors, memory-related errors, using GDB or LLDB. These are programs on your computer. So yeah, memory errors, they happen. What can we do about them? So we've talked a little bit about segmentation faults. That's your memory-related error. So also enjoy the old memes. So a segmentation fault, or a seg fault, is when your program crashes because it's trying to access memory that you don't have permission to access to, or it just doesn't exist, like the null address. So some things, like here's one example on the right here, like this that I'm highlighting. You can try and access out of the bounds of an array. So like this is an array that has indices from 0 to 2, and here we're iterating to index 3 inclusive. So if you print out the array at that address or at that location, it doesn't really exist. It's like past the array, so you could get a seg fault there. A lot of the time you might not, because your program still has permission to access that memory, but you really shouldn't be accessing it. We can go beyond it though. And then also another common example is dereferencing a pointer that points to some weird place or the null address. So here we're forgetting to initialize p, and if we go and we output the result of dereferencing p, that's following whatever random address this is currently pointing to, that's usually going to give us a seg fault, right? And remember that a seg fault is a runtime error, so you don't know if your program works, even if it just compiles. Okay, so that's unfortunate, but that's part of the game. So let's now go to my VS Code, and I've made two files from a long time ago, and here's one with essentially this first thing, this first idea of trying to read past the end of an array. So ARR3 doesn't exist. Let's see what's going to happen. I'll say G++. I'll do the full thing. Dash O seg fault 1 seg fault 1.cpp. And so what I'm saying is you might have access to that third phantom array element, and it just happens to be some weird value. A lot of the time your program does own ARR3, but it's undefined behavior to mess with it. Like if you set that, this could be some weird part of the C++, like the function that you're currently in, or like the function you're about to return from. Like this is random stack memory, and we'll talk more about the difference between the stack and the heap today. This is random stack memory belonging to some function. If you set this, this might ruin the rest of your program. You might get a runtime error later for some weird reason, because like you're setting a variable in some other function for, and that's just hard to track down because it's undefined behavior. Like anything could happen, anything goes. So okay, we have ARR3 at our disposal. What about ARR 50,000? Usually we're not going to have access to that one. So it doesn't exist, but this will definitely be past the end of our array in memory. It'll be past the all the memory that's been given to our segfault1 program. And we're even getting a nice warning from our compiler. It's nice to us. And oh man, do we read past the end of the array? Definitely on this line. So that's a problem. That's our first segfault. And then the next one, just don't look at the comment for now. I'll get to that in just a second. Okay, here again, in star p is undefined, probably null, and then let's output it. It could be some random value. A lot of the time it's null, but it doesn't have to be. It's undefined behavior, whatever that random value is. Fun stuff. Oops, segfault 2, please. There we go. And it just so happens to be some random value that is way past the end of our current program's memory space, or perhaps before it. So we don't have access to whatever this address is. All right, so you got a segfault. You're going to get plenty of them in your labs. Just get used to it. It's part of the learning process. How in the world are you supposed to debug? That's what I'm about to talk about. So to debug pointer related errors like segfaults, or just memory related errors, I guess. Runtime errors, because compiler errors, those will happen immediately and you can fix them. What do you do when you get a runtime error? Especially one that has to do with some random value of memory. It's a good idea to use what's called a debugger. The one that I'm about to teach you is called GDB. One debugger is called GDB, also known as LLDB on a Mac. Very similar, but slightly different. And a debugger lets you run your code in debug mode and outputs very useful information about, for example, the values of variables by name, the line numbers, where things go wrong. So this sounds too good to be true, but this exists. People have run into enough seg faults to make something like this. So here's how you use GDB or LLDB on a Mac. What you're going to do is you're going to compile this program with a special flag. We've been using O to like, please output this file as a special name, but -G takes nothing after it. It just exists. You got to say -G somewhere when you compile, just somewhere between the G++ and the end of this. Put a -G, and that tells G++ to compile your program with what's known as debug symbols, like things like line numbers, names of variables. So let's do that. All right, and then on your terminal, you're going to run the program inside of the debugger program. So you'll say GDB, then the name of the program that you want to run. All right, so on a Mac, though, I'll say LLDB instead. And when I hit enter, it'll start it up, and it'll be like, all right, I'm loading this program, I'm ready to run it. And then we can say run and hit enter. This is just like a terminal within a terminal. And oh man, does it run the program? It does what it was supposed to do, prints this random value. And then it says, oh, yes, we got a problem. It was a bad access. A seg fault happened. But look at what's it's even syntax highlighting, but it's pointing to the exact line where something went wrong. Isn't that beautiful? All right, and then that's some things that we can do in addition to just seeing where things went wrong is like to print out the actual value. So we actually, do we only have this one variable at our disposal? We essentially only have ARR. We can print out argc if we want to do, I guess. But you can say for any variable in the current scope, you can say print that variable. Like print argc for me, please. And it just happened to be 1 because we didn't run it with any other arguments. I can say print ARR, and then it prints all the things that it knows about. It knows it's a size 3 array. If I say print ARR 0, sure, that's 50. How about 3? That doesn't exist. It's that random thing. 4? Yeah, you're just getting random values. And if you go to 5,000 or 50,000, it's like, couldn't read its memory because we don't have that much memory for this program. That's beautiful. And then you can say quit, and then yes, we want to stop the program. We'll say Y and enter, and then we're back. So isn't that cool? Wouldn't that be useful in a future lab, this GDB or LLDB? So I've made some comments with all that information, and let's do the same thing now for this one. We will compile segfault2 with that -G flag to give those debug symbols so that it'll know which line number things are on and know the names of the variables. We'll say LLDB or GDB segfault2, and then please run it. And then, hey, again, we have the same kind of error, and we have an arrow pointing to the line number where something went wrong. So, oh, okay, that means, I guess, P. There was some issue with P, so let's print P. And oh man, was it null. So that's really going to come in handy. Please use this debugger on your own code when you get a seg fault. It'll tell you exactly where it happened, and you can print out all the values of the variables that would have affected the pointer or whatever you're trying to do. So you can print out all the context where the error, around which the error happened, and that'll be super helpful, I think. So please take advantage of a debugger. And then finally, just to go over this pointer arithmetic question, it's a bit hard to wrap your head around. We'll just talk about the problems again, see if you can convince yourself why everything else makes sense. But pointer plus pointer, it's like saying, I have a pointer to memory, P1, I have a pointer to some other memory, P2, it's pointing over here, it's pointing over here. And the addition of those two addresses, like this is 100, this is 200, Does 300 make sense? Like, that's just some random place down here in memory now. No, it doesn't. So that's why that's an issue, and we don't do those things. This is all pretty ugly looking. Let me just erase it because I have talked about it before. And then 5 is also an issue. Integer minus pointer. 5 and 8, those are kind of the same thing. Compare a pointer to an integer that isn't 0, and integer minus pointer. The idea is, remember that you never have access, or you never have knowledge about where something is going to be stored in memory. Remember that you never know where something is going to be stored in memory. And by where, I mean the address where something is going to be stored in memory. So you can't include any constants in your pointer arithmetic when you, or I don't want to say that because you can when you add like please go +1, +2. So you can't subtract in this way, and you can't compare a pointer. Compare, let's say compare to any constant address, any constant integer. Because you don't know if, because that just doesn't make sense, because you don't know where this thing is going to be stored in memory. All right, for that reason, you don't know where things are going to be stored, so it makes no sense to compare against some constant number, because you never know. Like, you can hope all you want that the address of your variable is going to live at, I don't know, address 452, but you have no control over that when your program is run. All right, so that is the first part of this, of these slides. And now I want to get into something known as the heap. This is the rest of this lecture is about this thing called the heap. And I just want to say, this is where the concepts stop for the midterm. So everything above that line will be is fair game for the midterm. From heaps onward, those topics from heaps onward won't be on the midterm. And I should say new topics, because everything builds on top of itself. So we're still going to be essentially reviewing by learning these new concepts, but I'm not going to be testing you on them until the final, okay? So this is now the heap, dynamic memory, no longer static memory. All right, so remember how memory looks, how we imagine it to look as C++ programmers. It's just a big table. It's like one big long array, and everything's right next to each other, and you can always get, you can index into memory at the byte granularity. So there's address 0, address 1 byte, address 2 byte. Go there and store something if you'd like. And each cell, so each like array element for this large array that is your computer's memory, has an address. It has an index where that where you can index into and store things. And remember that a lot of the time it might take multiple addresses to store one big thing. Like, so if I had an integer and my array started here at address 0, it would take the first 4 bytes to store one integer, right? It would take from address 0 to address 3. And then if this was an array and I had to store my next integer, that next integer would be stored in addresses 4 through 7 in terms of bytes. And we'll always usually talk about the starting address of something. Like the starting address of that integer was 4, even though it went all the way to address 7. And the starting address of this integer was 0, even though it went all the way to address 3. Okay, so that's the idea. And let's make this model more complicated. So let's pretend our memory is going from small addresses to big addresses. And then we have this large figure that I guess I should, let me see if I can just copy all of it, because it's quite interesting in itself. So this is how your programs are stored in memory. All right. At a very generic level, like at a very high level, this is how your programs look in memory. Though they won't get all of the memory, like they won't have all of the memory from address 0 to address all the Fs, because maybe you don't even have enough RAM to hit all these Fs. That's a possibility. Let's talk about what these different sections of the program are. You have your text section, your global data section, and then you have the stack and the heap. All right. Let's talk about all of these things individually. So I guess I'll just start drawing arrows. That might help. Boop. All right. So the text, and the RO stands for read only. You can't change it. Text section is for the actual program itself. So the machine code, the CPU instructions, they live in the text section of your memory and you can't touch them. The compiler makes them and you can't like change your if statement to a while loop while your program is running. That makes no sense. It actually used to be allowed in very old programming languages. We don't like that. You can't change anything here when your program is running. You wouldn't want to. So text is just the actual code. This is your source code. Okay? And then the global data is for all of your global variables. I need more room. Global data, or globals, is for all your global variables. They need to live for the entirety of the program. So they need a space allocated for them immediately after the program starts running. I'll just say immediately. So there's this section in memory because you've said in like your main function, things like that. If you declare a global variable, like something out here, like int x, double z, things like that. Those are global variables, and you can access them in any function, and they live for the entirety of the program, so we need to make space in memory for them to live forever. And this global data space, that section, is where those live. Okay? So your program instructions live forever, of course, because you need to run all of your program, and your global memory gets its own space. And then we have the final place inside of memory. At the very end, the stack we actually know. The stack we know already. It's your functions and their memory, and all the memory associated with them. Stack, you won't really need this unless you take like a assembly programming class. The stack grows down, we say, because it starts at a large address, and like every time you add things to the stack, like here's my current stack, I'm going to call a function, we actually like the starting address of the stack now, like the address right here is less than it was before, because the stack is growing from high addresses to low addresses. That's nothing I'm ever going to test you on, but it's just a fun fact. So the stack grows down, and it competes with the final section of memory, the heap. So the stack is growing down. The stack and this thing called the heap, which we'll talk about, they share this one section of memory. So the stack is when you're calling your functions, you're building up that stack and all of its local variable memory, all that stuff. And the heap is a place for dynamic memory, we say. And it's growing down. Oops. The heap holds dynamically allocated memory, we'll say. I'll get into what exactly that means, don't worry. It holds dynamically allocated memory, and it fights for space with the stack. So if ever, like the stack is growing up, 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 the heap is growing down, 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 if ever the top of the stack and the top of the heap cross each other, crosses the top of the heap, or vice versa, because one can increase and the other can stay the same, or the other can increase and the one can stay the same, doesn't matter, then your program runs out of memory. Okay, that's what it means to run out of memory. You've tried to allocate so much stuff that either you've blown your stack past the heap or you've blown your heap past the stack. Those are sharing memory space. All right, so that was a lot of just vague concepts. Let's get into what the heap really means. And remember, the stack is what we already know. It's the functions that are running and their local memory associated with them. All right, so that's the model. Okay. We've talked about a few things on this slide already now. So we have local and global memory. All right, so we talked about that. That was like stuff. Global variables live outside of any function. They live forever. And so let's say I have my main function. That's living out here on the stack, remember. Main, and it has like argc and argv. Those are its local variables. And the global variables, like stack globals, you can have other things like, I don't know, remember that I made that Harry Potter example? Those live forever, but the stack can immediately shrink when a function returns and that memory goes away. So the stack reuses itself. The globals live forever. So yes, we've talked about globals, the stack, and then I've introduced this thing called the heap that we don't really know what it does yet. And then, yeah, we have a bunch of different variable types now. So we have global variables, which can live outside of functions, like this. They're declared outside of any function. Local variables, which are declared inside of a function. Let's type all this, because why not? That's good to have. So local variables are declared inside a function. Global variables are declared outside a function. Dynamically allocated variables are these new things. They live on the heap. Can I copy that? Let's see. Oh, fancy. I don't want it like that, though. Dynamically allocated variables live on the heap. And then we also have parameters, function parameters. For the most part, you can think of as just extra local variables, because they belong to whatever function they belong to. So like if I had a function f, let's say, and that was this one that just returned, maybe it had a variable x and a variable y. That's its local variables. And then a parameter, maybe it had like a parameter a. It still lives on the stack with that function. Okay? All right. I think that's everything I want to talk about there. So the idea is we want to eventually talk about the heap. So I think, yeah, this was not yet talking about the heap. So take a second to just, using what you know already, take a good guess, or a very educated guess, as to which of the two functions we have, foo and bar. There could be a problem in both of them, actually. Which of them has a memory-related bug? So take a second to think about that while I go turn on my fan, because it's very hot in IV. All right, so I hope you made a good guess. Let us draw the stack diagram for both of these functions, because that'll give us practice with these new terms. All right, so remember that we have local memory, we have the stack, and then we also have global memory. So I'll draw both of them. So we have the stack, And then we have our globals, which live for the life of the program. So our global variable was called b. And that was a capital B, right? Yeah. Some integer. All right, then on the stack, let's say that in our first example, let's call foo from main. All right, so our stack would look like this. And then we're calling foo. Don't know what's going on in main, but they called foo for some reason. And then foo has a local variable called a. All right, so it's going to live in foo's stack frame just like that. And so really, we're up here. We're in the stack right now for main, and then we just called foo. It's growing that way. We're making new space for the functions that we call because they have local variables that need to take up space. All right, so there's foo with its a, and here's b sitting out there. And so we're going to set a to be 15, and then return the address of a. All right, set a to be 15 and return the address of a. Let's pretend the address is our favorite number. Let's put it in color, 100. And for fun, let's say that b is living at address 200. All right, so we're going to return to main 100, that address. So we're going to return the address of a. So that eventually main could set it again, right? And that's where the error happens, because you should see now that right when main gets back that address, it no longer has anything in it because foo's returning. And by returning, its stack frame goes away. Remember that. So when functions return, all their local variables go away. All their memory, let's say, goes away. So that's no fun. So you shouldn't have done something like this. You shouldn't have returned the address of a, because a is no longer existing back down here in main because we don't have this stack frame anymore. I hope that's clear. So that's an issue. So it's definitely could be a. It's not. We know it's not d now. And then let's do the same thing for bar. All right. So again, we have our stack and we have our globals. And for our globals, we still have b. And then for our stack, let's pretend that bar now is getting called from main again. We don't know why. It just wanted to call bar. Bar is going to do something important for main. All right, so it's going to set b to be 20 and return b. All right. No, sorry. Getting ahead of myself. B is not a local variable to bar. B is this global variable way up here. So we're going to set b to be 20. And then we can return from bar whatever the value of b was, which is 20. So there's no issue with that. And in fact, we could also return the address of b. Not a problem. If you wanted to do that, you would just be returning, I don't know, because its address is 200, right? You could totally return or 200. And main could index into that address because it still represents a valid place in memory because the global variables live forever. Those don't go away. They live up here in the global section of your program, and they're never going to be overwritten by new stuff like the stack might be. Okay? So I hope that makes sense. Please yell at me in office hours if it didn't. So that's the idea. So bar is going to return, and it might just copy the value, the 20, or you could even return the address of b, and you could use that address because b exists and it lives forever. It's a global variable. All right? So the answer then should be foo. Foo is the one that has the memory-related bug. All right? That's that. And now, okay, finally, let's get to this thing called the heap. We want to create an integer in memory, and we want to kind of make it be like a global variable. We want it to live for as long as we want it to live. We want it to disregard things like function boundaries. We want to essentially make a local variable that can live forever. All right. So we want to be able to make this kind of function that returns an int pointer, and it actually makes sense. Like it returns the address of an int that it created inside of itself, but is not about to go away when it returns. That's a lot of words. Let's talk about that. Do I have to? Oops. That's fine. let's talk about this. So the heap is for dynamically allocated memory. It's when you want to create a variable of a certain type, and you want it to live as long as you want it to. So you want it to live forever. You can control when a variable made on the heap gets deleted, or we call deallocated. So you're playing God on the heap. You get to make variables that live as long as you want them to. So they're kind of like global variables, but they can go away. So they're kind of a mix between global and local variables. But you are the garbage man. You get to determine when these variables that you're making that live on the heap, when those get recycled and deallocated. All right, so that's the idea. So we want to write a function that creates an integer in memory that we can use for as long as we want it to. So we're going to use this keyword, this brand new keyword, and it's called new itself, okay? Let me go to this slide to make sure that this is all looking okay. All right, so let's make a program now. So let's say the heap, or let's say heap.cpp. All right, let us include IOStream using namespace std. Does this tell me how long it's been recording? No, it doesn't. Int main. All right, so then we have main, and let's return 0. And all right, we do want to write this this function eventually. Int create an int. So this is our goal. We want to, inside of this function, create an integer on the heap, okay? Make it live on the heap and return the address of it so that main can continue to use that integer. All right, so it's like a local variable, but it's also like a global variable. So to do that, we use the new keyword. All right, so this is what we're going to do. We're going to say return, or let's actually spell it out. So int new int equals new int, just like that. All right, and the types are not yet correct, because whenever we say new and we give it a type, it's going to return back a pointer to that thing. All right, just bear with me, and I'll explain exactly what I'm doing here. So new, you can think of it like a function. It takes one parameter. It takes a type as a parameter. All right, and it returns back the address of something of that type on the heap. So it's made something brand new for you on the heap that is an int, and it tells you where it was. It tells you its address, and we can store that address and set that thing there, okay? So that's the idea. So let's return now new int. And you could have really just done this in one line, say return new int please, but I want to show you this in a diagram in a second. And then that variable lives for as long as we want it to. So let's get the new int. So int star, I don't know, let's say I equals create an int, please. Make an int on the heap. Let's do stuff with it. Let's set it, I equals 42. Print it out, maybe. That's always nice. So now we're done using I. Let's delete it. And just like new, there's a keyword called delete that takes a pointer to something on the heap and gets rid of it. All right? Delete takes a pointer. You can think of it as another function. a pointer to something on the heap and deletes that memory there. Deletes the memory at that address. All right, let's make that all pretty. There we go. All right, so we're making a brand new integer on this thing called the heap. We're setting it, printing it out, and then we're done with it. So we'll delete it. And that's kind of your strategy whenever you're using the heap. You want to make something for yourself, and then once you're done with it, you should delete it. Technically, it's all going to be deleted when your program ends, but we are good programmers. We're taking care of our memory. We're managing it. And notice, though, that you can keep on passing around this address, this int star, this thing that we just made. As long as you keep passing it around, you can use it in any function. And it's just this one place in memory. It's this integer that you can always use. All right, so enough words. Let's talk about this in a diagram. So here's main. I actually think I want a bigger main. Might need to move this down in a second, but we'll find out. So here's main. So it has only one local variable, I, and I is a pointer. And it's going to hold whatever we get back from this function called create an int. We'll just call it create int up here. And this function has a variable called new int. That is a W with an underscore. Wow. New int. You know what? I'm just going to rewrite it. New underscore int. And that itself holds an address of something that we're about to make on the heap. And yep, I do need more room. On down you go. All right, so here's our stack. Oh, hello. Stack. And now here's this place, this brand new place where things are made, called the heap. All right, so what we're doing in this function is we're making a new int on the heap and returning that address and saving it inside of new int. All right, that's our goal. So when we say new int, what happens on the heap is we make space in memory for one integer. And it is fresh and it is brand new, and we just made it out of thin air, so like it's shiny. Okay? That is your brand new thing on the heap that you just made for yourself. So this is an int that lives on the heap. It has no name, so the new keyword just returns its address to you, for you to use that instead of some kind of name. All right, and then you can give it a name inside of a pointer, right? So let's say this is at address 100. So new int now is going to hold the result of making this brand new thing on the heap. It's its address now. It's going to hold the address of that integer called 100, all right? And now the beautiful part is like how this is very similar to a global variable, because once this function returns, create an int, it's going to return back this address, this new int address, which is 100, remember that. It's going to return it back to main, 100, that is an arrowhead, excuse me. And it's going to set I to be that address, right? So that's what we're returning. We're returning back that new integer, placing it inside of I. If you think I'm going slow right now, it is just to drive the point home. It's very important. So now I is another pointer on the heap. And what just happened is create an int returned, right? This is gone. Right after it does its returning job, it did everything it needed to do. There's no space. Now all this gets reclaimed, right? It goes all away. Pretend it's in red. Now, main can still talk about this place on the heap because it lives as long as we want it to, until we delete it. So main can go and can set it to 42, not a problem. And then once it's done with it, or whatever function it gives it off to, once it's done with it, you can just say delete I. And what happens then is now it goes away and you should never use its address ever again, all right? Then it becomes what's called a dangling pointer, which we'll talk about in just a few slides, I'm sure. All right, so actually let me put this way up here. This int lives until you delete it. And delete, remember, is a keyword, right? So at the very end, we are deleting it, so I'll just draw a red line like that. Okay, so that is our example, and let me actually compile and run it for you just to make sure it's all working. Make heap. So it's doing everything we talked about. Making that brand new thing on the heap, giving it back to us so we can use it. Set to 42, and we're done with I, get rid of it. All right, so that is the heap in a nutshell. You're going to get a lot of practice with this, don't worry, this is just your first encounter with it. And now, let's get a bit fancier. So here is another kind of function that, again, makes something. We would like it to create an array of integers for us to use later. Please take a second to determine whether or not it's doing the right thing. All right, and so you have now made your best guess. Let's pretend again that this function is being called from main. All right, so again, oh darn, I can't scroll down unless I draw something. There we go. So here's our main function. It needed to create an array for some reason, so it's going to call it. There's an E there. It's going to call this create array function. This is the stack, remember? And it's going to make an array. And so the key is it's all type checking. ARR is the address of the first element of this array, so this is going to return an int star, totally fine. Is it correctly creating an array of integers, though? Well, the answer is no, because it's not making a brand new array that lives out here, all shiny and nice. It's making a local array, isn't it? And we know what happens to local variables of whatever length we gave it. Maybe it starts at address, I don't know, 300. Let's be adventurous. That's ARR. It's going to return 300, but oh man, address 300 does not exist after that function returns. That's no fun. So this is incorrectly creating an array of integers. You can create arrays on the heap, and that's the way you get them to live forever. Okay? So we should fix that. Let's see here. I think we'll get to that in just a second. Yes. Actually, not really. Let's do it now. So what this function should have been is this. Int star create an array. And remember that the type of an array can be int star. It's not a problem. So it's going to return an array. I guess it takes a length. So let's make a pointer to the start of an array on the heap. That's a mouthful. You can use the heap to make arrays too. So you can say things like let's see. New int, and then give it the size, just like that. So let's skip all the extra stuff. We'll say return new int of that size. So this returns a brand new array on the heap. It'll return the starting address of it. Returns the starting address of that new array. All right? An array of integers on the heap. So that's what it should have been. And instead of giving you an example of that, let me just prove that it compiles. And let's have a bit more fun. Let me briefly just check ahead to make sure that I'm not messing up anything here. No, okay. So let me move on for just a second to this slide, and then I think we can successfully do that next example that I want to do. So here is essentially everything we know already. You can use this new keyword to create something of a certain type on this thing called the heap, brand new, and things are referenced on the heap by their address. So we get back the address of this thing. You can't really give a name to something on the heap. And what that does is it goes into this section of memory and it takes a bit off. If there was a bunch of this cloud of things that we allocated already, let's allocate one more thing on the heap, and that's growing down, or sorry, up in terms of lower addresses to higher addresses. And it's competing with the stack, remember? So that's what the heap is doing. And then once we're done with that thing, we give it, we give a pointer to that thing on the heap, again, because we can't give a name to anything on the heap. We give that to the delete keyword, and then that'll go into the heap and delete that thing. So then we can reuse that address the next time we say new something else, new double maybe, or another new int, why not? So that's what new and delete, they kind of come in pairs like that. And before we talk about this issue, let me give you a fancier example with creating arrays on the heap. So we'll also get some examples or some practice using our structs as well, because that's useful. So actually, let's see how much of this I can copy. Dun dun dun. Let us make on the heap an array. Not of ints. That's too boring. Let's make some points. So remember what points are. It's got a double x and a double y. Or you can have 3D points, why not? Let's actually have 3D points. Let's go crazy. Let's make an array of points on the heap. I don't know. Let's make an array of 3 points on the heap. So remember that an array can either have an array of points, let's say, or let me just say it like this. An array of points can look like, in terms of the type of an array of points can look like point array like that. Or sorry, that's Java. Point ARR or point star ARR. These are equivalent. In fact, and heap, for the heap at least, it's always going to return a pointer to something, so you can't really use this syntax for the heap. We have to use this kind of syntax for an array on the heap. So we'll say point star ARR equals new point, and then the size of that array we want on the heap. So we'll say 3. So now ARR points to the first element in that array on the heap. So in essence, what we're doing now, we're in main, way down here. We just made ARR, which is a pointer to this place on the heap. This is the stack. This is the heap. And I'm probably going to want to move this in a second, but that's okay. We just made an array of points, and points are fancy, they're large. So let me make a large array here. We have 3 of them. And right now they're all undefined. They all have x values and y values though. X, y, and let's give those values just to drive the point home. So let's say ARR 0 equals, I don't know, 1, 1. Then ARR 1 can be, we can set it in the opposite way. I can just do the, oh sorry, it's got to be x, y, z, doesn't it? Well, I ran out of space to draw this, so let's just stick to x's and y's, I guess. We'll say x equals, I don't know, let's make this 2, 2. And then ARR2 can be 3, 4. All right. Now let's make a function to compute what's called the centroid of the points. And what a centroid is it's just the average x value and then the average y value. So let's make a function that does that. So point centroid point star ARR, and then because this can also be an array, this kind of type can also reference an array. We also have to pass along the size. And so the centroid is the average x value and average y value. somebody in data science can tell me why this is important to have. But this is the concept, and this is a good example. So we're going to take an array, and we made it on the heap, and we can use it just like any other array now. Okay? So we can see out the centroid of this array of size 3, but it is itself a point. So let's make a print point function. This is just an extended example using arrays that we made on the heap. And we could use references so that we don't have to copy anything. Let's actually use a const reference because we don't want to change that p. See out that, and then the x value, and then a comma and a space, and then the y value, and then a new one, and then let's have a new line as well. All right, that's print point, and now all we have to do for centroid is this. So let's call this centroid.cpp. So let's get double average x and average y, and let's start them out both at 0, 0.0. I kind of like spaces in between those things. Let's do this. All right, we've got average x and average y. Now let's sum up all the points and then average them. All right, so for int I equals 0, this is good review for everything. I is less than size I plus plus. I'm iterating through this array. Let's sum up all of our x's, so average x is whatever it was plus our current indices x value. And then the same thing is happening for the array of y's, or the y parts of that array. And then we have to, let's see here, we have to divide average x, because now it's just the sum. It's whatever it was divided by the size, and then the same for average y. And then now we need to make a return value that is a point, remember. So let's point, I'll call it ret for we're about to return it, and let's say it equals average x and then average y. All right, so we're going to return that pointer, that point that we wanted to return, called ret, and that will hold the centroid of all of these points that we passed along. So like the graphical representation of this is we have a bunch of points. Here's one, here's another, here's a third. Like the centroid is kind of somewhere over here, I think. You kind of average them together, and that's helpful for machine learning. All right. And so if I want to draw what's happening inside of this program, again, I have x's and y's all over the place. I think it was 1, 1, 2, 2, and 3, 4. So this array is shiny. It lives on the heap, remember? Shiny and new. And we're using it inside of our centroid function that we're calling from main. And then eventually we're also going to call print point, but I did not give myself enough room for that now, did I? And so centroid itself also takes the array and its size. So ARR is again pointing to the same place because we passed it along like that. And then size holds 3. So this is when the centroid function gets called, this is the contents of both the stack and the heap. All right? And then we're going to take that result and give it to print point, but let's worry about that later. All right. Why is that complaining? Did I not use namespace? I did. Let's find out. So remember, because I'm doing this kind of initialization, or sorry, this kind of initialization, we have to compile with the C++ 11 standard. I have to say G++ centroid.cpp-o centroid standard equals C++ 11. And let's see what I did wrong here. Oh, I'm sorry. This would have made sense if I returned a string, but the print point function prints to cout already. So this is really all we wanted to do. Excuse me. I can say /centroid, it'll print out the centroid of these 3 points right there. 1, 1, 2, 2, and 3, 4. So it's 2 and then 2 1/3, looks like. Beautiful. All right, so that's an extended example. But there's one thing that I forgot to do. Because I'm a good programmer, I have to remember to do it. I have to delete. Now that I'm done with ARR, let's delete it. So the syntax for deleting an array on the heap is slightly different. We say delete, then brackets, because we have to make sure that it knows that it's an array that we're about to delete. Okay, that's all. Instead of delete for an array. And that'll make this array on the heap go away. All right, that's the idea. Delete. You have to use delete bracket bracket when deleting an array off the heap. All right, and that lets the memory that was associated with that array get reused for new calls to the new operator. All right. So I think, well, of course that won't change anything. We can recompile, rerun. Let me just make sure to put this in a comment up top so that you know how to compile it if that ever gives you an error, because you might be used to not compiling it with this particular standard. And yeah, that's a fancier example. And with that, let's go into these concepts now. You can have a lot of issues on the heap as well, because they're just another place to go wrong with pointers, right? So you can have something called a dangling pointer, first of all. And a dangling pointer is when you have a pointer that's pointing to something that no longer exists. So we had some good examples of that already, actually. We just didn't take advantage of them. So let's say I made int star I equals new int. Let me draw both the stack. Let's pretend we're inside of main. I won't draw any more boxes. Then also the heap. So here's what's happening. Int star I equals new int. Sure, star I equals 42. So here we have I. This is an I. Let me draw like a script I so that this makes sense. Looks nice. So here's our I. It's a pointer to something on the heap that we made, and we're setting it to be 42. All right, that's normal. Let's say we're done with I now, way down here. We'll say delete I. Whee. And so what happens when we say delete I, let's say that this was at address 100, this is address 100. Well, when we say delete, it gets rid of this place in memory. But I is still a local variable. It's completely separate. After this delete, it really wants to capitalize that I for me. I is still a local variable holding an address that doesn't exist anymore. That place on the heap, it's undefined behavior to access something that's been deleted. It's undefined behavior to access a pointer, access an address of memory that has been reclaimed when you call the delete operator. All right, so that is an issue, and you should not do that. That's what's called a dangling pointer. And then another issue that you can have is what's called a memory leak. And it's also sometimes called tardy free, and tardy is in like you're late for class tardy. But I'll pretty much always say memory leak instead. And what this means is we've been very careful to not have any of these, but it's any kind of heap memory that's not deallocated. It's not called delete on before the end of the program. So I almost messed up here. For one run of the program, I did not call this delete function, this delete operator on array, so it was technically a dangling pointer. And so that's what happens when you don't clean up after yourself, or you just run out of ways to even access something on the heap. So that's a bit complicated. So let's talk about that. Let's do this. Let's say int I equals new int. This is a memory leak that I'm about to give an example of. Again, we have the stack and we have the heap. So here's I, and it points to this thing on the heap. And we can say, I don't know, star I equals 42 again. Why not? Then we can say I equals new int again. See what I'm doing here? So I is no longer that pointer. It's not a pointer to that place anymore. It's a pointer to this brand new place over here. Whee. And let's say star I now equals 43. So I hope you followed along with that. And the issue now is that old place in memory. We have no way of reaching that old that first int that we made on the heap, the one holding 42. We have no way of getting to it. We lost our only way of getting to it, which was that address that we held in I initially. So now I is pointing way over here, and we have no clue where this place is in memory, and that's what's called a memory leak. All right? This is like the textbook example. This is a memory leak. These are hard to trace. It's really hard to track these down, so please make sure you're always calling delete. Like you should pair them off, new and delete. Those should always come in pairs. All right, so what we should have done before doing this line, we should have called delete on the initial value, this initial I. So right here, if you put a delete I right there, you would have solved the problem. This problem could be solved by putting a delete I right here. All right, I hope you see that. So then we still would have had access to this I, that address right there. Okay. Just a couple more slides, and that's it. So this first issue is one last question regarding memory leaks. So take a second to determine whether or not this example function results in a memory leak, this foo function. All right, so again, let's draw the stack, let's draw the heap. That's going to be second nature to you eventually. Let's pretend we're calling foo from main. So this is the stack, and this is the heap. All right, so inside of main, we're calling foo, and foo has a local variable called p, which holds a pointer to some new integer that we're making on the heap. All right, and then foo returns, right? It's a void function, it returns absolutely nothing, it goes away. But oh man, did I also lose access to, just like that last example, this place on the heap, this address. I only knew about it through p, and I just got rid of p by returning from this function and not giving back the value. So you could solve this problem by giving the address that p held back to main, so that main could take that address and maybe like access it, use that variable if it wanted to, and eventually delete it. But right now, it's doing none of those things. So if foo returned p, or if only foo returned p, then we would not be in an issue. Okay, so that is indeed a memory leak. So we lost access to something. So it was the second kind, heap memory that can no longer be accessed. That's the more common kind. All right, 2 more slides. Which of the following functions returns a dangling pointer? And remember that a pointer that is dangling is something that points to a memory location that no longer exists. All right. So, what do you think? Well, F1 is creating something on the heap, which is quite nice. And it's returning the address of that thing that was made on the heap. So that means that there is no issue with F1. In graphical form, we have our stack, we have our heap, and let's say for main, we're calling F1, it has a couple local variables. It has num and mem1. Don't know what num was, but that's okay. It's that size of that array that we wanted to make for ourselves. And mem1 is a pointer to the start of that array on the heap. It's an array of size num, whatever that was. Some dot dot dots, let's say. And so when we return back from f1, we're returning mem1, which is the address of this thing. So we're essentially, if I can put a box for what we're returning the address of that array. So that's not an issue because now in main, the main can hold on to that value and still access that thing. All right, so that is not a dangling pointer. If main just called this function and didn't assign its return value, then it is. But we're going to say that it's not, and main does the right thing. F2 now, it goes back to that same issue. So where is this mem2 array being created? It's being created on the heap, isn't it? And even though we return a pointer to its first element, that element and that whole array, in fact, goes away. Okay, so again, I think I can more or less, no, let's just do it all over. Stack, let's see, heap. We had our main function. Now I need a very large F2. And it had num still, num and mem2. There's num, and here is mem2, this long array. There it is. And so we're going to return an address, the address of this mem2 array, which is like, if I could draw a box for what it's being returned, it's a pointer to that thing, but that whole place, this place in memory right here, it's not supposed to be an arrow. It's about to go away when F2 returns, you know? So this is a dangling pointer because we're trying to return a pointer to something that doesn't exist. All right? So it's in fact only F2 that has this problem. Okay. And then finally, I just want to give you a quick overview of something that you're going to be doing in your homework 7. You're going to be writing a fancy struct to hold like students and their majors and their GPAs for all their years. Apparently all of these students are seniors, so you're going to make an undergrad students struct, and you can make it so that anything's in any order, but apparently in this order the name is first, then the last name, then the major, and then an array of GPA values for each year. And your job is to create a print function for this thing, and it should go through and iterate through this array of undergrad students. And for everything, we print out something in some nice, pretty way, and also calculate the average GPA, and that's the big deal. So how might you do this thing? So let's say I had this undergrad students struct called UG. How do we get at all of those elements? You'd loop through it, and you'd be like for int I equals 0, and so on. And now we're down here, or we're in the trenches of the for loop. If I wanted to get something out of this UG array, we'd go UGI, and then maybe you want to get its name, right? You could have something like that. But things get a bit fancier when you need to calculate maybe the average GPA. Inside of this struct, you have an array, okay? Which is fancy, but it's okay. What happens, you just need to follow the types. So UGI gives you an entire undergrad struct, all right? So this is it will give you one undergrad student's struct. Sure, that works for now. Then you could say something like .gpa. And this all together, that's the first one, this all together will give you the array of GPAs for that one student. And then you can index into that even. You could say like the sophomore year GPA, all right? That's exactly what I want to hopefully makes more sense now. Just keep on using the dot operator, and eventually things will work out. So the first thing, this is the whole undergrad students thing. This is the Gpa array inside of the undergrad student struct, and this is a single element inside of that array inside of that struct. And now this arrow doesn't make a lot of sense. The array of GPAs. This is a single GPA now. I hope that makes sense. So just that you'll be chaining a bunch of dots and brackets, and I just want to make sure that that makes sense. And remember that you'll have to compile with C++ 11 if you want to use this fancy initialize after you've already declared kind of syntax. All right, so that was everything that I wanted to talk about today. So remember that everything from here onward is only on the final. So from heaps onward, I will not be testing you on this midterm too. Okay, I will see you next time.